so now we're ready for part 5. And I know that you were saying to yourself, but Mr. Eric, where was the mathematics? I love using my calculator. I love plugging numbers in and solving it for all of these different formulas here. So I want to do that. Okay, so we'll do it. So you can put your pencils down at this point because this is in blue, which means that this is kind of optional. No, don't leave me. Okay, so come back. Okay, so this is important because I want you to see how you can mathematically figure out what should be the speed of the bowling ball when it gets to the bottom. And then once you got that, then you can calculate these two energies. So I want you to see where were the numbers coming from in the simulation. So we're going to begin with the moment of inertia. We have to go back to here and find the bowling ball. Okay, you see it's a what? It's a 2/5. Okay, so on your calculator, 2 divided by 5 is 0.4. So we're going to start with that the moment of inertia of the bowling ball is 0.4 mr squared. Okay, next we're going to take that and plug it into this formula here. So that we've got 1/2, and instead of the letter I, it's going to be 0.4 mr squared, and then we still got omega squared. Okay, now the next thing that we're going to do is we need look at this piece right here, and do you remember that velocity was equal to r and then omega? So this was the connector between omega and v was the r. So look, what can we do? We could plug that in to right here, and that would be v squared. And so now we've got 1/2 mv squared, and but you still have that 0.4 on there. So I flip-flopped it. So I took this over to here and I took this over to here. So why did I do that? Because if you look at this piece right here, that is the kinetic energy when it is going sideways, and then when you multiply it by 0.4, that's the kinetic energy it has when it's rotating. So let's take a look down here. So now we're down to this thing. So we've just figured this part out right here. Okay, but the total energy, so E total, has to be the sum of its kinetic plus its potential. So E, I'm sorry, it's going to be E kinetic translational plus E kinetic rotational. And we know that the translational is 1/2 mv squared, and we know that the rotational is this one here. So now we're just going to combine everything, and it turns out to be 0.7. So if you want to try that, go ahead. So now you got the total, or the kinetic energy, is equal to 0.7 mr squared. Who cares? So how can we use that now? Okay, now we're going to use conservation of energy. So conservation of energy says the energy that you start with has to equal the energy that you end with. So what kind of energy did we start with? It was potential energy. So it was mg and then h, where h was the height that the bowling ball was released from. What did it turn into? So at the bottom of the ramp, the potential energy turned into kinetic energy. So we're going to set this equal to 0.7 mv squared. Potential energy equals the kinetic energy. Now look at what we got, an m and an m. So what happens? The m's cancel out, and so now you got gh equals 0.7 v squared, and then take the square root, and now you've got that, so that the speed at the bottom of the ramp is going to be equal to that. So if we wanted to, which we're not, thank goodness, but that's what you're thinking, I'm sure. But if we wanted to, we could take the v from the simulation here, and then we could plug it into this equation, and then solve it for h, and then that would have been the height that the bowling ball was released from. Because if you look at the simulation, I don't see it. So it doesn't say on the simulation how high the bowling ball was released from. But we could calculate it now. And then we could also calculate these two numbers. So this one's the translational, and then this one's the rotational one. And we could calculate those two energies and verify that they were correct. Are we having fun? Okay, that's good. So now let's go down and look at our post-lab questions. What was the purpose of the lab? So you should be able to write that down. What is the official unit for an angle? So write that down here. Convert 180 degrees into radians. Okay, so I showed you how to do that with the two parentheses. Okay, then convert 3 revolutions into radians. So again, 2 parentheses, and then do whatever it takes to cancel the word revolutions, and then you'll end up with radians. Okay, number 3. A wheel has an angular velocity of 0.9 radians per second, and it rotates for 2 minutes. Through what angle did it rotate? So we're going to be using that the idea that omega is going to be equal to the angle over time. So we know what the omega is, so that's the angular velocity. Now the 2 minutes is in the wrong units, so you need to convert that to the correct unit, and then put it in there, and then solve it for the angle. Where should you sit on a merry-go-round if you want to have maximum linear velocity? Okay, so go back to where we had a formula that connected the linear velocity to the angular velocity, and that should tell you. Question 5, what would be the sign for an angular acceleration if the wheel was slowing to a stop? So remember your sign convention. So what sign should you use if you want to have an acceleration that will make something come to a stop? Number 6, what is the moment of inertia? What properties of a rotating object does the moment of inertia depend on? So what letters does it depend on? Number 7, a torque of 10 newtons is needed to turn a nut, and you have a 0.5 meter wrench. How much force do you need to exert? So there's going to be a formula for torque, and then it's also going to involve the radius and the force. So use that one to solve that question. Question number 8 is to state Newton's second law of motion for a rotating system. question number 9 is the same torque is applied to two wheels. Wheel A has 2 times the mass of wheel B. So this one might be a good idea to draw a picture so that you got wheel A and then wheel B. And so it says that wheel A has 2 times the mass. So wheel B has a mass of that, and wheel A is going to be 2m. They both have the same radius. Which is going to have the greater angular acceleration? So you're going to, first you need to write down what's the formula for Newton's second law of motion. Okay, it's going to be the same torque is acting on A and on B, but they're going to have different moments of inertia because they have different, okay? And so all you got to figure out is which one has the larger moment of inertia. And then put that into your Newton's second law and figure out what would that do to the angular acceleration. Be very careful. Okay, then we got 10. A cylinder has a moment of inertia of 3, and it's spinning with an angular velocity of 100. Convert 100 rotations per minute into radians per second. So that's going to require 2, or actually 3 sets of parentheses in order to do this one. And then calculate its angular kinetic energy. So if you know it's omega, and if you know it's I, then you can calculate its kinetic energy. Now you are going to, well, it's a cylinder. Okay, so that's telling you what the radius was. So the important thing is that you know its moment of inertia. All right, and then calculate its angular kinetic energy. So that's it. So we got one more lab left to do, and then we're going to be finished with these simulated labs. So I will see you next time.